thought we will continue with the calculation part of the reaction equilibrium for single reaction. We saw that we have Ka, which is a function of temperature alone, that can be easily seen from the right hand side, which is and we saw if we restrict ourselves to pure component, steady state, then we can write this in terms of the standard Gibbs free energy change of reaction. So K is a function of temperature alone. We saw how in the table we can calculate the standard Gibbs free energy at 298.15 Kelvin, and how using specific heat data as well as the enthalpy change at 295, standard enthalpy change, we can obtain the standard Gibbs free energy at any temperature other than 298.15. So once we have done that, then we come to the left hand side and complete the calculation, which would basically involve calculating the equilibrium extent of reaction or the equilibrium conversion. So for that, we saw that Ka becomes Kf by the standard state pressure raised to the power of delta nu, which is the difference in the stoichiometric coefficient, the sum of the stoichiometric coefficient on the product side minus the absolute value of the sum of the absolute value of the stoichiometric coefficient on the reactant side. So this then becomes K phi Kz times P over Pss. So what we saw, what I was pointing out was, this is the mole fraction equilibrium constant, the capacity based equilibrium constant. Now what we assume is that apart from the temperature and pressure, the initial number of moles of all the components in the reaction is given. So from that, we can easily get Z J, that is the mole fraction of component J, at any time during the progress of the reaction. Specifically what we want is the equilibrium mole fraction, or the mole fraction and equilibrium. Right? So this is something that can be obtained as Ni by N total, or by the sum over. And we have seen how each of the mole numbers, they are not independent, they are all dependent on each other, they can all be expressed in terms of the extent of reaction. So that becomes the only variable. So effectively, I can write any of the mole fraction as a function of the extent and N naught, which is the initial mole number vector. Right? So that is what we have. So K phi can be expressed in terms of epsilon N naught. P is given, Pss is known. The reaction itself is given, so I can calculate this. Now K phi is pi I equal to 1 to C phi j or j raised to the power mu j. So phi j we have C, again, if it has the coefficient component j in a mixture, is again a function of P, P and Z, that is the mole fraction vector. So again, K phi can be expressed as a function of P, P and epsilon and the initial number of moles. So what we get, so I have this, so this I am going to equate. So K phi times Kz, this is a function of temperature and pressure, which are usually specified, and the unknown extent of reaction. Kz is again a function of the unknown extent of reaction. Pressure is given. So everything is given. The only variable is the extent of reaction. That has to be equated to the value of Ka that I have calculated at the given temperature of the reaction from the tables and various other data. So this becomes a simple variable epsilon to be determined in terms of the, or determined from the single equation, which is basically coming from sum over j equal to 1 to purpose is this whole equation has come from that, plus certain conventions and so on. So you have to understand that. So that purpose is clear, and we will take up one of these problems that is there, namely ammonia formation. It's a standard problem. So what we will do is see how to calculate it. From now on it is very straightforward. I'm sure you have all done at this level, I mean at the BTech level or the MTech level, the calculations. So calculation will be simple, but you have to understand the whole picture in mind. What is the principle, what are the definitions, how the standard states are defined or specified by convention, what the tables give and so on. That's the last 3 lectures are mainly to refresh your memory or enlighten you on that. Calculation aspect is something that I'm sure you can all do quite well. So what we have here is that first calculate the equilibrium constant at 298.15 and also the equilibrium constant at 800 Kelvin. So for that, first I need to calculate assume the ideal gas standard state, which is standard state 1. So delta G reaction at 298.15 is all I can calculate directly from the tables, right? And that would be, it will depend on some of the tables I found a slight discrepancy in the numbers, so you have to, the answers that I have given will depend on which tables you use. I think these numbers reflect the tables from YBC law, but I found that they're somewhat different because everything is going to go in exponential, so the A value will be a little bit different. So what we get is this is nothing but 2 times G Ig NH3 at 298.15 and 1 bar. That is the standard state pressure that is there in the table. And N2 and H2 is simply 0 because they are all elements and they are simply assigned. Right? You have to see how arbitrary. It seems a bit arbitrary to assume those to be 0, but we won't get into that now. Maybe later on, if I have time, I can explain. It really doesn't matter. Right? So this is what we will take in your Approx. So now this value from the table in YCC law is given to be minus 16.747 kilojoule per mole, and so so that is what it is. So maybe that is roughly 33 point something. I don't have the final value, but you can easily calculate that. It's 33.4. Now an easy way to calculate, so from this I can calculate KA at 298.15 is exponential of minus of this, so you have to be very careful about the sign and express everything in joule per mole. That will be 333,494 minus sign I'm taking into account. So KA is exponential of minus R would be 8.314 and times 298.15, and so that turns out to be 7.383 times 10 power 5, a very huge value for equilibrium constant at 298.15. So we use a Smith and Van seems to have given minus 60.45 only. If I do that, I will actually get you can easily per mole.
But we are already multiplying with 2.
Huh?
We are already multiplying with 2 mole number.
Yeah, 2 times minus 16.747.
2 is the number of moles.
Yeah.
For that.
G is minus 16.747.
Kilojoule per mole into mole. So the final should be this
No,
one.
it's not mole, this is stoichiometric coefficient. This is stoichiometric coefficient. Right? So it will be per mole only. But you can check, this is the value you get. Right? Is it correct? Okay. And so, let's leave it, let's not worry about simple values. We'll just take this as whatever it is, wherever I got this from, this is the value. Now, the delta H reaction at 298.15 is again 2 times the enthalpy is minus 46.055 kilojoule per mole. And so that becomes minus 92.11 kilojoule per mole. That's a very highly exothermic reaction. So Ka at 800 Kelvin, approximate value can be Ka at 298.15 times exponential of again minus 92.110 by 8.314 times 1 over 298.15 minus 1 over 800. Yes. So this factor. Huh?
Delta K reaction per mole of which one, sir? Nitrogen or hydrogen or ammonia? Delta K reaction.
Yeah.
First one, sir. Per mole of which one, sir?
Per mole of ammonia form. Okay, so that is the value from the table. So stoichiometric coefficient is 2, so I just have that, right? So same thing with the enthalpy of formation of ammonia. And so then the answer I am getting here, you can easily calculate it. Right, is very low. It is 5.556 times 10 power minus 5. You can see almost an order, 10 orders of magnitude lower because of the exothermicity of the reaction. This is always a trade-off for exothermic because the equilibrium conversion will decrease actually with increase in temperature. As you can see, the equilibrium constant is decreasing. The equilibrium conversion will also decrease, but because of the fact these reactions have to be carried out in reactors with certain optimum size, we cannot also keep the temperature very low. So if the temperature is low, the equilibrium conversion might be very high, right? With the final conversion that we can obtain. But the rates will be so low that we will need enormously huge volumes of reactors. So that is the trade-off for exothermic reactions between kinetics and equilibrium. So anyway, we have just taken an 800 Kelvin. Basically, anyone should know how to execute properly. Now, the answer that I have is taking into account the temperature. This is ignoring the temperature dependence of the enthalpy of reaction. I'm simply treating this as constant. This is the approximate formula. The correct answer which we will use in our calculation, which I have got from taking account all the specific heat data and so on, is slightly lower, even lower actually, 1.122 times 10 power minus 5. That's a very low. So that's what we have to operate. So it is given 3 or 4 subdivisions. So I'm going to take up now the problem coming back to this side. So we now assume that it is an ideal gas mixture. That's the first simplification that we will make. I will simplify the calculation. So I will bring it as ky. So ka is ky times p over pss times delta u. For ideal gas mixture. But since I am taking gas mixtures, I am taking the mole fraction or denoting them by yi. So now the delta mu here is clearly is equal to 2 minus 1 plus 3. So it's actually minus 2. So we have ky times pss by p squared, because it is minus 2 p over pss. So I'm taking it as pss by p squared. So now all we need to measure can vary from subdivision to subdivision. PSS is 1 bar, you have to remember. So we have to, by using P, it has also to be converted to bar. If I'm using PSS equal to 1 bar. So KY is clearly YNH3 squared by YN2 times YH2 whole cube. As we pointed out, the KY or the KZ is here 5, we made it 1. So ky is simply a function of the extent and n naught. So we have to find that, what that function is. That's all there is for the problem. So easiest is to set up what is called as a stoichiometric or mole number table. So I'll treat the reaction here. Then I will start with, let's say, the initial mole number of, this is a mole number that should not be confused with nitrogen. So, mole number of each of the components is the initial, T equals to C. At any other time, value we wanted at the equilibrium is actually T going to infinity, but at any other time, it would be, you can easily apply the, now we will express everything in terms of the conversion rather than the extent. I always find the extent because it has the units of mole numbers, whereas the conversion is dimensionless. So x into is definitely very familiar from reaction engineering. The conversion, especially one of the reactants, we choose it as nitrogen, the limiting reactant here based on the numbers that are given. It's always going to be nitrogen. So NN2 by NN2 naught. So now the first thing is NN2 can be immediately written as NN2 naught times 1 minus XN2. So first thing I have accomplished that, and clearly NH2 would be NH2. Now this is something that we have all done in reaction engineering courses, so it would be fairly straightforward. So 3 times the number of moles of N2 that have reacted. So this would be minus 3 times N2 naught minus NN2. So that's the easiest way to remember. So the number of moles of hydrogen or any other component other than the one I have chosen to define the conversion would be the, if it is on the reactant side, it would be the initial number minus, right, the number that has of nitrogen that has converted and times the stoichiometric coefficient, because for every mole of nitrogen, 3 moles of hydrogen would have reacted. So that's fairly straightforward. So now I will write this in the following way. I write it as NN2 naught. I'll take it out as a common factor so that it looks very similar to this. So this would be NH2 naught by NN2 naught minus 3 times, right? So NN2 naught is taken out, so that would be 1 minus NN2 by NN2 naught. So that would be X. So this I will simply call it as X. This is X N2. Right? So that is what we have. This I will denote as alpha, so this will be n into naught times 3 into x only. 3 into x, right? So let's just write this again, n into naught times n h2 naught by n into naught minus 3 times 1 minus n into by n naught. So this is clearly x. So what you're saying is correct. So it's alpha minus 3x. Similarly, I can write nh3 as n into naught times, I'll call this as beta. The beta is nh3 naught by n into naught.
That's right.
And then it would be plus 2x. That can also be easily shown. Now, the common mistake that I always find students make is that they simply equate y nh3 to n nh3 and do the calculation. That will lead to errors because here, especially this delta v is not equal to 0. So first I have to calculate n total at any time. Because if I want to calculate the mole fraction, I have only calculated the mole number, so I need to calculate the total mole numbers, right? So now if the delta v is 0, the contribution coming from the total mole numbers in the mole fraction expression will all cancel out. You can easily verify that. Here it won't happen because we have 2 moles here and we have 4 moles there, right? So you will clearly see that that will not happen. So n total is nn2 plus nh2 plus nnh3. So this will be nn2 naught. I can take it that as constant 1 minus x, constant factor rather, plus alpha minus 3x plus beta plus 2x. So this is going to be n into naught times 1 plus alpha plus beta minus 2x. Right? So this kind of alpha and beta and all that is not really required. It will just give you one problem where there's a given ratio of alpha and beta, you can directly do it. If you're having to do series of problems, it's probably easier to write it in this general form. So now we can easily calculate. So y nh3 is going to be n into naught times beta plus 2x. N into naught is going to cancel everything. So 1 plus alpha plus beta minus 2x. Y nh3 that is. That's y n2 is 1 minus x divided by 1 plus alpha plus beta minus 2x, whereas y h2 is going to be alpha minus 3x divided by 1 plus alpha plus beta minus 2x. So this is what I need, so I can sort of erase all the intermediate calculations and simply have ky, which I have here. This is ky. Right? So ky is equal to beta plus 2x squared divided by, write the final nth term separately, beta plus 2x squared, y n2, I will get 1 minus x times y h2 the whole cube would be alpha minus 3x whole cube. And so clearly here I get an nt squared and here I get an nt power 4. So if I do that, so I get an nt squared term on top in the numerator. So this would be 1 plus, I mean this this is the term coming from here. So 1 plus alpha plus beta minus 2x, the whole square. It will now come in the numerator because the denominator is divided by this for 4, whereas the numerator is divided only by that quantity 1 plus alpha plus beta minus 2x squared. So you get that extra square term on top. So this is what we have finally. So now what we have is that whatever that we have calculated 1.122 times 10 power minus 5 at 800 is to be ky, all of this. So I can write it here. We have to have the correct ky times ESS by P square. So let's take the first problem that is given, and which is the temperature is common for all the subdivisions, and so the first one that is given is that pressure is 1 bar. And the initial is a stoichiometric mixture of N2 and H2, no NH3. Initial mixture. So we need only the ratios. The stoichiometric mixture should know what to do. The alpha is actually what? Alpha is NH2 naught by NH2 naught. That's important to keep in mind. So what is alpha here? It is a stoichiometric reaction. It is simply 3. Right? Alpha is 3. So N2 plus what we have here. Right? So 3 times the number of moles of is the stoichiometric, so it's in the same ratio as the stoichiometric coefficient. That's what it means. By saying the initial is a stoichiometric mixture, right? So this is equal to 3. No NH3 means beta equal to 0. So I now have 1.122 to the 10 power minus 3. P is 1 bar. So P over PSS is 1. So that pressure won't contribute, pressure term won't contribute. So what I have is 4x squared divided by 1 minus x, and alpha is 3. 3 cubed will be 27. It will be 27 times 1 minus x whole power 4. And then again, alpha is equal to 4 minus 2x whole square. So solving this, I can probably slightly simplify this as whatever it is. It's one easy way is to take simply the square root. So if I take the square root, but anyway, this might be in some cases a complicated problem. If I take the square root, I get 2x and 4 minus 2x by 27 by 1 minus x squared. I'm sorry, not 27, it is square root of 27. We take the square root of both sides. Then this will lead to a quadratic equation, right, in x. That is easier to solve. Right? So that should be easy to solve. And the answer that I am getting, if you get 2 roots, I don't know what about the second root, but the answer I have here is that the one root property that matters is very low. So this is clearly not a very feasible condition. Okay, either is going because the pressure is very low. So next is, so you can calculate, you can work out the quadratic equation and you can easily calculate, but it's a very small quantity. Now the second part says same as 1, but pressure is equal to 100 bar. So then I get 1.122 to 10 power minus 9. The same thing, 4x squared and 4 minus 2x squared. 27 times 1 minus x 4 power 4. However, now I am going to get a big contribution from here. So this is 100 bar, 100 by 1 raised to the power 2. Right? So it's 100 squared. Effectively, the equilibrium constant. So this will now be 10 power minus 1. 1 by 10 power 4, right? Yeah, because it's minus 2. So PSS is 1 bar and this is 100. So 1 by 10 power 4. And so if I take, so this is what it is. And so if I take the 10 power 4 here, then it will become 10 power minus 1. So it's 0.1122 is equal to all of this. So again you are going to get a quadratic equation, and the answer I have, this is also given, is I'll let you solve it and also look at what the other root is. Does it make any sense of something negative or greater than 1 or whatever? Okay? So this is the advantage with X, because the extent of reaction depends on the number of moles, so we don't want to really deal with it. The X is 0.165. So clearly with the increase in pressure, now this is a very famous statement of the Chatelier principle, so called, the exothermic wave already seen, D logarithm. That's another part, the temperature part of right. So if this is negative, then the equilibrium constant is going to decrease with increasing temperature. So decreasing temperature for an exothermic reaction will, or rather an increase in temperature will push the equilibrium to the left, rather to the reactant side, which is what we have seen. You look at the 10 power 5, sorry, this is 10 power minus 5. Yeah, this is 10 to the minus 5. But the earlier one we had was 10 raised to the power 5 at 298.15. So that can be taken as one aspect of the Chatelier principle. So here you can clearly see that the general expression has to do with Ky. That is what you have to calculate. So because Ky is what is going to give the equilibrium conversion. So that is how you are to interpret the other part of the Chatelier principle with respect to pressure, because Ka we know is a function of temperature alone. But now I can write this as Ky is equal to Ka, a function of temperature, times PSS by V raised to the power delta mu. So delta mu is negative, as is the case here, right? So an increase in pressure will lead to an increase in Ky, and it will shift the equilibrium towards the product side, which is what we are finding at 100 bar. So the P is appearing in the denominator. So if delta mu is negative, then clearly as delta mu is less than 0 implies that Ky will increase as P increases. Right? Because then I can write this in the numerator P raised to, we can further write it as Ka of E by minus, if you want to bring the pressure in the numerator. Right? So clearly, if delta Q, maybe you clearly see here, because there is already an inverse and then a negative. P raised to the power minus delta Q. Right? If delta Q is negative, then minus delta Q is positive. So Ky will increase with increase in pressure. It can be very easily seen. So that is what people, it's normally stated as if there is a decrease in the number of moles from the reactant to the product side, which is what it is. That makes delta V negative. Then an increase in pressure will shift the equilibrium towards the side having the lesser number of moles. That is how it is said. For me, it is very easy to interpret it from this equation here. You can clearly see, numerically you can see, it's a P raised to the power minus delta mu. So that is what Ky is. Here we look at Ky. Because the larger the value of Ky, we can expect, probably can be shown, the larger will be the value of the equilibrium conversion. Right? So that is what is happening. You can see it numerically verified. Now the second, the third part has to do with the same as same as 2, but effectively alpha will turn out to be 5. And same as 2 alpha equals 5. So the number of moves from N2 to H2 is 1:5. That means alpha is actually 5, right? Instead of 3. So in which case, the x, so alpha is 5, so that would mean that the whole equation would we get 1.122 to 10 power minus 1 again, but this now is going to change. These equations are going to change. So this is the same, 4x squared by 3 minus x. So it's going to clearly push the equilibrium to the right. Using more of the hybrid. This is one way of pushing the reaction to the right. And so we have here 1 minus x, and this is now going to be 5 minus 3x the whole cube. So 1 minus x is going to be a bit more difficult to evaluate numerically because they don't get the 3 into 1 minus x out, and so this is 6 minus 2x the whole square. And as you can see from the answer, the easiest thing is to substitute different values. So we know this is going to be greater than, I will let you solve it numerically. You know it's going to be greater than 0.16, so you can just try different values of x greater than 0.16 and finally match it with the left hand side. So that's one way of quickly doing this. Or if the answer is given, you can easily verify whether the equation is correct or not by simply substituting the answer. So clearly more of H2 is shifting the equilibrium to the right. The last one is again 4 is same as 2. That means pressure is 100 bar, but alpha is 3, P is 100 bar. But now beta is not 0. So given that it is 0.1, right? Beta is actually 1. So we have some amount of ammonia to begin with, and clearly here the Xc is going to decrease. So you have more ammonia, it's going to shift the equilibrium to the left again. More of the reactants will shift the equilibrium to the right. When you start with more of the products, it will shift. This all can be regarded regard as different aspects of the so-called Chatelier principle. So when you do that, right, so then now the equation will turn out to be again 0.1122 is equal to the 0.1 plus 2x squared divided by, this is going to be 27 times 4.1 minus 2x squared. The beta will get added, and the answer that is given is x equal to 0.1236. So we can now tabulate all of this and look at what are the various effects that are happening. Because all of it is the same temperature. You can do the same thing at the lower temperature, but we saw that the equal conversion will be very low. So we just take this temperature 800 Kelvin, and then I just list out. So we get alpha first, and then we have beta. So alpha is n2 naught by n. Alpha is nh2 naught by n2 naught. This is nh3 naught by n2 naught. And then we have the pressure, another variable. And then we calculate x. Right? So alpha is 3. This is also 3. We have 5. Again 3. So this is 0. This is 1, 2, 3, 4. Beta is 0 to go, except for the last one, the beta is 0.1. The pressure is at 1 bar, 100 bar, again 100 bar, 100 bar. X we saw 0.002. So clearly this case is of very little value, very low equilibrium conversion. 100 bar we saw it's around 0.165, 0.236, 0.124. From here to here, you can clearly see the effect of the pressure, quite dramatic. 100 bar of course is a huge increase in pressure, but here it is magnified because the delta V is -2. So it's 100 squared is the way the equilibrium Ky is going to increase. So that has a dramatic effect. Right? So here we see the effect of increase in the number of moles of one of the reactants. Right? And if you compare these two, we see the effect of having more product. But another measure of the efficiency of the whole process, the conditions on the equilibrium can be given by calculating the number of moles of energy, because after that's also a final objective, how much of ammonia is actually formed. And here you will see that the first one is very low. So you go back to the formula that we had for YNH. You can also calculate the final composition of the reaction mixture. So what we've got is X. From that you can calculate how many moles or how much is the mole fraction of each of the components. And so this would be, this turns out to be 0.09, clearly a big improvement, but still not very high, but because the conversion itself is quite low. And for here, even though the equilibrium conversion is quite greater, almost 1.5 times more, but the number of moles of ammonia is smaller, obviously because of the huge amounts of hydrogen we are using. So even the shift in terms of conversion, the fraction, the initial nitrogen converted, because we are using more of hydrogen, the mole fraction of ammonia is turning out to be smaller. So you have to again worry about whether you want higher conversion of the final value, because if you want want to separate out, we obviously want a higher mole fraction of ammonia to be present. From that standpoint, this is probably a better condition. Again here, we see the conversion has decreased, but the mole fraction of ammonia remains the same. That's because we are using some extra ammonia to begin with. That also gets added. We can probably see how much of ammonia has been created out of the reaction to truly measure how efficient the reaction is. So when you make these comparisons, you have to keep in mind that here there is initially a certain amount of ammonia, but even though the conversion has decreased, that is simply whatever percent is also added to the final composition. So it's not really a true reflection of how much ammonia has been formed out of the reaction, right? So when you look at absolute values of the mole fraction, you have to keep that in mind. These clearly bring out the main features of the pressure has a major effect. Other effects are relatively minor, increasing the number of reactants or amount of reactants or products. Are there any questions? So you can similarly go through the other problems are very similar. So I don't expect. Main thing is you have to do it without making a mistake in these cases. This is make the maximum source of error, and also negative and positive kilojoule and joule that can make a huge difference. In if you find the calculation of the equilibrium constant is wrong, then everything else will be meaningless. Yeah, you can have a for example, if you miss out a 10 power 3, you can easily see factor this way or other in the exponential. You can see how much effect it will have on the equilibrium constant. You have to do it correctly. That is more important than worrying about whether it is complicated or simple. It is simple calculation, but you have to do it correctly, right? So this is we will see the next 4 lectures. How I want to proceed, I still haven't decided whether we consider combined reaction and phase equilibrium or do both.